Ladies and gentlemen, welcome to CERN, the largest laboratory in the world. My name is Claudio Rosmini. I work as a science journalist for Euronews, which is following this live event today through its social network. I'm very happy to be here, and I hope you really appreciate this amazing science show.
Thank you, Claudio, and welcome very much to you. Thanks to Euronews for this fantastic partnership for one more of our lives from CERN. This one is a special one. Today is Open Days at CERN. It doesn't happen every year. It's a very special opportunity to visit locations in CERN that are not normally accessible for visitors, and also to see and participate in great activities, fun activities to learn physics, engineering, and this was one of them, and technology, with great fun. It's not a bad explosion, it's just a balloon, don't worry. So we are here in the test area where the superconducting magnets of the LHC are tested for cryogenics. They are just behind me, and this is just one of the locations that are open for visitors who have come from all over the place. Thank you to them. And this live is for you who could not come and who are following from home because you're far away or because you could not attend. And we are here for you. You can ask questions. Claudio will collect the questions, and together with the fantastic science guests that will come on stage, they will answer all your questions. Please start posting them on all the social media platforms on CERN, be it Facebook, Instagram, Twitter, and YouTube. In the meantime, I'm off, together with Cédric, on an exploration tour of the site. And believe it or not, Claudio, if everything works, cross fingers, we'll be live from underground, from 150 meters underground, from many fantastic locations of CERN. If everything works, because we are live and things can go wrong. So I trust you to hold the show because you're a professional from Euronews. Thank you. I go, and I'll see you in a moment on the screen, hopefully. Ciao, ciao.
Ciao, ciao, Paola. Bye-bye, Cédric. So today we are not live only on CERN, Facebook, Twitter, YouTube and Instagram, but also on Euronews digital platform. And this is going to be an interactive show, and during the live you can ask a question to CERN scientists who will be here on stage with us. And while Paola is leaving for her tour of the facilities, I'm very glad to welcome our first guest, CERN Director for Accelerator, Frédéric Bordely.
Good afternoon, Claudio.
Welcome on stage, Frédéric. Paola has just left for an exploration tour of CERN, starting at the source of the bins, where all particles start their trip inside CERN Accelerator Complex. What happens there?
All is coming from a bottle of hydrogen. Very simple.
Very simple.
An atom of, you said that. An atom of hydrogen is very simple, is a proton and an electron. Then we are using this gas, we have to extract, to expulse the electron to get a proton. Then we have this gas from this bottle going through a source, and with electrical field we extract the electron and we inject the proton in the LINAC, linear accelerator, what it is the first phase acceleration.
It sounds simple, but I'm sure it is not.
Definitely, there's a lot of technology to do that, but in the principle, it's simple. It's this bottle of hydrogen, thanks to Mr. Avogadro, 10 to 23 mole, you have a lot of hydrogen for our accelerators.
Okay, and now we have the unique chance to see the very first stage of the CERN's accelerator complex, where particles start their trip at the speed of light. Paola is right there, I hope, at the LINAC 4.
Claudio, I'm at the very start of the proton circuits, where the particles are injected in the entire CERN accelerator complex. Everything starts from this bottle, a hydrogen bottle, from which the protons are extracted. Let's find out how. I'm reaching Alessandra now, just behind, at the very source of all the particles, all the protons in the CERN accelerator complex. Follow me. And so after the source, there is a whole array, I can see, of incredible different instruments. What are they?
So the RFQ, bunchers and choppers. We've got a drift tube LINAC here, 27 meter to 50 MeV.
So this is a lot of technical terminology. Basically, you have many different instruments To do what? To bring the protons from 0 speed to how much?
Half of the speed of light. That's how fast we inject the proton into the booster. And that's all thanks to this RF cavity. So until here, it's the same energy as LINAC 2. And here we go on and we increase further and further the energy. The secret, as I said, is RF cavity.
So it's amazing. In just a short distance, you can go half to the speed of light already in the very first stage of CERN's accelerator complex. So you said the secret is the RF cavity.
Secret is the RF cavity with a very good gradient and functioning very well.
Object here.
Which is this object here, exactly.
Okay, that's great. So behind us, next step is the booster, the proton synchrotron booster is the next stage. And Claudio, I'll see you there in a moment. For now, thank you, Alessandra, for this super short but really intense guided tour of LINAC 4.
Okay, thank you all.
Thank you, Paola. It was very, very interesting. So, Frederic, if I understand well, the linear accelerator, or LINAC, is the source of all beams for the CERN accelerator complex, right?
Definitely is a source for all the proton. We have another LINAC for ion, special ion, LEDs, and so on. But it's a source for all the proton, for all the experiments at CERN, including, obviously, the LHC.
And can you explain us what's the next stage? What is following this moment?
Okay, so we have a lot of accelerator, chain accelerators. After this LINAC, and by the way, what you saw is a new LINAC you will put in operation next year. It is a new one, completely new, 50 meter and so on. It's going to the booster. Booster is a synchrotron, 150 meter to accelerate from the LINAC to go to the proton synchrotron. Then we have a chain of accelerator because you cannot inject the particle directly, for example, in LHC. And all these chain accelerators are accelerating the proton for LHC, but they have also their own physics. Then the booster is a very dedicated machine, accelerating from 160 MeV to 1.4 2 GeV next year, and passing to PS, but having also their physics, we will see later, Isolde is extracted from the booster.
Okay, and Paola has arrived right there into the booster. A very unique opportunity to see this machine. Let's see.
Inside the proton synchrotron booster, it's only 15 meters underground, but it's a real privilege to be here in this machine because it's not part of the circuit of the Open Days visits. It's especially for you who are following us live remotely from Facebook. This machine is very special because it's the only one at CERN with its 150 meter circumference that has 4 stages, 4 beam pipes where protons are accelerated, one on top of each other, like a donut. It's been operational since 1972, but this year is going through a major overhaul of many of its components. So we're going to discuss that briefly with one of the people in charge of this overhaul, Mauro Paoluzzi. Welcome, Mauro, to the CERN Open Days Facebook Live.
Hello.
So you're in charge in particular of this system, the radio frequency system, which accelerates the beam. So what did you change?
Exactly. So this is the new RF system of the machine. What changes is basically everything. We have a brand new system that covers a very wide frequency range and uses modern components. And basically what it does is increase the extraction energy of the beam from 1.4 GeV, that was the energy of the last operation month, to 2 GeVs.
So you're going to be more powerful beam, more energetic beams. And this is not the only change in the machine. You change many other things.
Yeah, there are many components. In particular, the injection system is completely new. We change kind of particles that we inject.
And I guess I understand it was made in a collaboration with Japan.
Yes, Japanese gave a valuable contribution to the RF system upgrade.
Very good. So this shows how CERN is global. It's not just European. There's all the countries participating here. And I'm very glad now to give it back over to you, Claudio and Frederic, to talk more about this machine and the next acceleration stage. And I'm over to one of next acceleration stage. See you in a moment.
Wow, that was really, really interesting and amazing. And Paola, you are running very fast. You are like a particle. But now, for the moment, let's remain in our Explore session. I remind you that you can ask questions at the end of each session. And now, let's continue our exploration inside the CERN's accelerator complex. Frederic, once the particles are produced, and start their trip in a linear accelerator and then accelerated in the booster. What happens next?
Next, we go to the proton synchrotron. It is a machine, an accelerator of 600 meters of circumference. It's a historical machine of CERN. CERN was born in 54 to build this machine, was put in operation in 59, is still in operation, that we are doing maintenance, upgrade, and so on. But this machine should run and should be operated at least up to 2040. And it is a one objector of SPS and LHC, and also having their own physics.
I'm sure that Paola is running faster than a proton in the LHC, and so I think she's there right now. Let's see what the acceleration cavity looks like.
And let's continue our exploration around the LHC accelerator complex. We are here at point 4. This is one of the 8 points around the LHC ring. There is no collisions here. It's the deepest cavern, more than 150 meters below ground. But here something very special happens. All the particles passing through here get their kick, and they are accelerated to close to the speed of light right here. Let's take a look. Okay, this is a Spanish-speaking group. We are following them. There are many languages spoken at CERN, and visitors come from all corners of the world. And now, getting ready before an underground visit, people need to put a helmet, because these are the safety rules. I'm wearing myself safety shoes. It's a workyard, basically. We are going inside the LHC machine tunnel. This is really a great privilege as well, only possible on open days for visitors. And we are going in the deepest cavern, 150 meters below ground. So it's the first time you go down the LHC?
Yes, I visited once Atlas experiment, but it's my first visiting, because if I understood correctly, we are going to be in the cave, in the tunnel. In the
machine, in the tunnel.
Inside, in the tunnel.
Right.
I'm pretty excited.
Say that again.
I'm pretty excited, yes. A bit scary.
Este sería nuestra zona de seguridad, y por eso esta puerta está cerrada. Es lo único que está cerrado. Entonces, vale, adelante.
This is the place where particles are accelerated. Everybody knows magnets. Magnets are not used to accelerate the particles, but to keep them in the track, to make them curve and to keep them straight in the straight sections and make them curve in the curved section. Where they are accelerated is here, is the only place in the LHC machine where they get the kick. And this kick is given by something that we're going to see right now, called the radio frequency cavities. So Marta, do you work here?
Yeah, I'm working for an external company, actually.
Okay, but what do you do?
So I'm in a technical office, and I do the electrical studies. So the electrical installations for the machines and the experiments, that's me, yeah.
That's great, and today you're guiding.
And today I'm guiding. Yeah, that's it.
Thank you very much. Here we are in the LHC tunnel. It's a little bit difficult to recognize the LHC machine because we are used to blue dipoles, the magnets, but this is not a magnet place. This is the only place in the machine where we have a special instrument, the radio frequency cavities. They are contained inside these vessels that refrigerate them to their operational temperature of 1.9 Kelvin, so super cold, the coldest on Earth, basically. And the only thing from the LHC that you can recognize really are these two beam pipes that carry protons in opposite directions up to their collision points in 4 points around the LHC. These cavities, they have the task of accelerating the beam. The beam arrives from the SPS ring into the LHC, and every time they pass through these cavities, they get an acceleration up to around 7 tera electron volt, 14 times the injection energy from the SPS. So it's quite impressive. Over to you, Claudio, to talk more about the radio frequency cavities, and see you at next point.
Definitely, Paola ran very, very fast. I want to say hello and welcome also to our audience, the CERN audience, but also the Euronews audience. We are connected together on Facebook, on Instagram, on Twitter, on YouTube. So I want to remind you that you can send us your question, and our scientists will answer your questions at the end of each session. But okay, we have seen an accelerating cavity. but acceleration is not everything. What are the other components? Where do the particles travel? And how can you steer them inside these big machines?
As I was explained, we have electrical field, radio frequency, cavity to accelerate the beam. To guide the beam, we need magnetic field. Then we have these magnets, dipole to guide the field, to keep the particle on circumference. We have also a lot of quadrupoles, because it's not only one proton, it's a bunch of protons. One bunch in LHC is 100 billion of protons, and you have to focus them. Then we have dipole, quadrupole, and we have a lot of series, a zoo of magnets to correct all these things. In LHC, we have close to 10,000 superconducting magnets to guide it and focus the beam.
Wow, impressive. But what happens after the acceleration to the speed of light?
I want to say, it was said, at the LINAC 4, you are half of the speed of the light. But after the SPS, the PS and SPS, you are at the speed of the light. When you are entering in LHC, you are already at 99.99% of the speed of light. It's a slight increase of the light, but it's not so much the speed. We are putting energy in the particle. All the goal of an accelerator at the end is to put energy in particle, to smash them, and to transfer this energy in mass, and to look at, in the big detector, what are these new particles created by this smash of proton.
Okay, quite clear. Let's now see what happened to beams once they are in the LHC at the speed of light. And why do physicists need these accelerated particles? What they do with them? And let me introduce Freya Blackman, particle physicist and member of the CMS collaboration. Hi, welcome, and nice to see you here. So it's your moment now, because we have this tough question. So why do physicists need to accelerate this particle at the speed of light, and what they do with them?
Okay, so there is multiple aspects to this. So for one thing, there is an equation that most people might have known of. It's a very, very famous equation by Einstein, E equals mc squared. And what that means for us is that we can use the energy of the particles in the Large Hadron Collider to make other particles. And some of these particles are very rare. And this is why it's always important that we are also upgrading the Large Hadron Collider and all the pre-accelerators, which is what you saw before, because we want a lot of collisions. Most of the things that we are interested in, for example, the Higgs particle, is very, very rare. The LHC beams, they collide like every 40 million times per second, so it's every 25 nanoseconds. But most of those collisions make particles we already know and have studied before. So here you see some actual collisions. This is a collision where we think a Higgs particle was produced. And what you see there is that actually all the different particles that are produced, we try to record with our detectors that are put around the collision point. And this is what you will see later when we go to some of the experiments, because these are very, very large 3D digital cameras that take photos of these collisions. Now, the interesting thing is that every collision is different. In every collision, different particles are made. And the rare ones, the ones that we are interested in, they only happen extremely rarely, which is why it's so important that we collide enough, 40 million times per second.
Wow, very, very interesting and well explained. Now, let's see where Paola is right now. I guess she's arrived at CMS.
Wow, 100-meter deep pit. This is real exploration inside CERN Accelerator Complex. We are at CMS, the compact muon solenoid, 100 meters below ground. Let's go. Okay, so exploration starting in the lift.
Okay, everybody,
just move towards the back of the elevator, please. CMS.
This is the bypass tunnel. And here we are, 97 meters below ground to be precise. This is the fabulous compact muon solenoid. It's compact compared to the other big detector around the LHC, the giant Atlas, but it's still very, very huge. It's 14 meters high. And this is the birthplace of the Higgs boson. Actually, the particles, the beams coming from the LHC collider, just collide in the middle, right there, in the middle of the detector, around 4 points. This is one of the 4 points. And then from the energy of the collisions, physicists can photograph, basically, take images, very special ones, with these huge detectors of the particles and the new physics phenomena that emerge from the energy of these collisions. It's quite exceptional to be here right now. It's fantastic. You're going to ask questions to the guests, physicists on stage. I can only share for now with you the excitement of being in the birthplace of the Higgs boson and many more particles and many future discoveries. So many visitors already. What's your job today?
My job today, in the beginning, in the morning, I was a guide for 3.5 hours, and I guided 3 groups. And now I am a crowd marshal, so I have to make sure that we can process or allow as many people as possible to visit CMS, and we're very excited that we can host so many people during open days in CERN.
That's great. So I said before, you are counting visitors as if they were particles. This guy, CMS detector, how many particles is it counting per second?
A lot. So per every 25 nanoseconds we're producing about 20 particles, and it happens 40 million times every second. So everybody can do multiplication and get with a very large number of 1 billion.
So it's as if it was a 40 million photography per second, 40 million photos per second. It's amazing, this detector.
It is indeed. So we still would like to see 1 million visitors, not 200 million as a target for this visit, just to match the number of particles which we're producing in a second.
Hi, hello, my name is Paola. What's your name?
I'm Harry.
Hi, Harry. Do you like visiting CERN?
Yes, I do. It's more interesting than what I would be doing at school.
Yeah, that's a great answer. Thank you. Good luck for the beginning of school year. Thank you. Have a nice visit. Thank you very much.
Yes, Paola, but we also have a nice and funny audience right here in front of us. And I welcome you again, and thank you for being here. And also, thank you for following on all the social networks, CERN, Facebook, Instagram, YouTube, and also on the Euronews social network, the same, Twitter, Facebook, YouTube. And you can keep on sending us your question. The CERN scientists are here to answer your question. And this is the first session Q&A, so question and answer. So we have some questions just collected by our social media staff right here that I want to thank for their collaboration, for their help. And let's start by Freya. We have a question coming from Besim. Do dark matter and dark energy really exist?
So, well, let's start at the beginning. The reason why we know that dark matter exists, or at least the effect of dark matter exists, is because in astrophysics, which is different than what we do at CERN, but they build big telescopes and things like that, they have actually measured in multiple ways that there is other matter in the universe that is not like the atoms that we know, and that is called dark matter. So we know of all the things in the universe that we know of, our matter is only like 20%, and the rest is all dark matter. Now, I'm a particle physicist, so of course what I would say is, well, the rest of this matter should of course be particles. And if that's true, then it's very, very likely that we in some way at CERN should be able to see it.
So let's move to the second question, again for Freya. It comes from Lee. Is anyone working on finding the quantum solution to discover the graviton? Wow.
That is indeed a very good question. So we look for many new particles, and this is why it's so important that we have many, many collisions, which is what we're making sure will happen during this upgrade. Because if the graviton exists, And then we can use the mathematical models that describe it to also predict what would happen in the Large Hadron Collider collisions. Now, we already know that the differences would be very, very subtle. So for that, we need a lot of collisions to actually study that and see if there's any evidence of this.
And a third question for you, coming from Kuladip. He says 90% of atom is empty. So how solid matters are built?
That is a very good question. So there are three forces that keep these atoms together. And depending on where you are in the atom, there's different particles that are sort of gluing or attracting the particles together. So the electron is spinning around the center of the atom, the nucleus, and that is mostly electromagnetism that keeps it actually in its charge. Well, special quantum physics electromagnetism, but still electromagnetism. Now, the particles inside the nucleus, so inside the center of the atom, they are kept together by a different force, which is called the strong force. There also is the weak force, which is responsible for radioactivity mostly, and the fact that the atoms are stable. And all those together work together as a team, and that team we call the Standard Model. And that together describes why everything sticks together. Because indeed, most of the atom is empty. I think it's actually a lot more than 90%.
Okay, now it's time for Frederic to answer some question. One coming from Instagram, Christiani. Is it true the world would blow up if something goes wrong at the CERN?
No, it's not true. Not true at all. It's true that we are storing a huge energy in the magnet. You can see magnet as you have the blue one behind us. We have 1,232 in the machine. The stored energy in this magnet is 10 gigajoule. Maybe 10 gigajoule is not every day your cup of tea, but it is the kinetic energy of a big Airbus A380 at 700 kilometers per hour. That's the energy. Then what if you have any problem? We have to extract that energy in 1 minute. But this is energy is locally and is not so huge for the things. And LHC is 100 meters below the ground level. The energy stored in the proton, all the proton, is 700 megajoule. Is the energy able to melt 1 ton of copper? We have to take care because it's not so good if we are spreading the energy on our magnet. But for the population 100 meters above, there is no problem at all. And this, I can say, the LHC is super safe for any people in the population. By the way, when you are in operation, nobody have access to the tunnels. And all is remote, all is derived by the control room above on the surface.
And you can trust Frederic. So another question from Sharon through YouTube. Are you guys trying to make neutrinos too?
Good point. Very good question. We are not doing neutrino physics. It was a few years ago. We had this we call European strategy for high energy particles. It was a decision. CERN is definitely high energy physics laboratory. And we had a discussion with American and also Japan. They are doing physics for the neutrino. They have some physics. CERN is doing what we call neutrino platform. We have a neutrino platform close to here, where we are looking detectors. We are paving the way for the experiments that will be done in US and in Japan. And I think it's a good example of sharing the means between all the continents. US and Japan will do the neutrino physics. We are preparing for European neutrino platform for the detector, R&D, and so on. It will be transported later in US and Japan. And CERN is the unique place for timing in the world where we are doing high energy physics, let's say high energy with a proton and maybe later for electron, positron.
Okay, thank you very much for these answers. And we are a little bit in late, so we have to accelerate. We need a booster.
We know to do that.
We move toward the next section, the future. Let's see the clip. So Future is the name of this session, but it's also the reason for having an open day now in September 2019. In fact, all the experiment and the accelerators are switched off because you guys are preparing the future somehow. So let's start by Freya.
Yeah, indeed. So I already hinted at this. So we have been studying these collisions, and it turns out that with the intensity that we have of the Large Hadron Collider now, we would need many, many, many years to actually study really rare particles. So we've asked our friends at the accelerator division of CERN if they could make more collisions. And they said yes. So that was really, really wonderful. And of course, this also means that we need to make sure that these cameras, these detectors that you saw underground, where that little boy was enjoying himself so much, that those detectors are prepared for that. Because more collisions means that photos get much more busy. And we, of course, want to have very, very precise, very accurate photos. And for that, we need to have more precise cameras. So more precise detectors.
Frederick, do you want to add some few words about this?
Exactly what was said by Freya. Now LHC in this present form will run up to 2023, and we have a big upgrade of LHC to squeeze more the beam, to put more proton in one bunch, to increase by a factor 10 the number of collisions. Then what they expect for us is more collision, because as she said, Freya, you can find in all this very large number of collisions new particles. Just to one number, you need 1 billion of collision to get 1 Higgs. And for maybe dark energy particle, you will need billion, 10 billion and so on. Then we need that. Then this is the first phase. And after that, we are looking what could be the post-LHC machine. But we will discuss that later. Then I think it's very good at CERN. It's very safe, sane. When we have operation of existing machine, we are project and high luminosity LHC, HLLHC, what we are doing, is a project approved with a cost completion project. A delivery will start in 2026. It will run up to 2040. And after that, we have studies to look at what could be the machine after the LHC, the post-LHC machine.
Okay, now thanks to all this information, we can start a journey into the future by looking at the place where the future is being built right now.
And here we are in a place where the future has already started. This is a special workshop where many components for the high luminosity LHC are being prepared to go very soon into the LHC tunnel. I'm here with Isabelle Behar, who works in the high luminosity LHC projects. Hi, Isabelle. So, where are we?
We are in SMA2. It's a very special place. It's a place where we are finishing the most part of the components. In this case, we are cryostating the different dipoles and preparing all the components that we are going by this shaft that you see just there. It's called PM2, and is the last moment for the magnets. We are downloading them so that can be installed in the real part in the machine, in the LHC tunnel.
So what are the main components of the high luminosity project that we can see here that you are getting ready?
Well, here we have only a few, because you know that high luminosity, the main, since the strategic moment is going to be in LS3. But you see here, you have a collimator. This is going to be installed.
Closer.
Yes, let's go to see it. So this collimator is specific for us, and it's going to be, you see that there's two different components close to it. There are the connection cryostats. They are going to go with this configuration, but also with, you see this other cryostat there? Yeah. Blue, but more dark blue than the usual one, is going to be for the 11 Tesla, for this magnet that is one of our flagships of high luminosity.
So you said two things, collimators and magnets. Magnets we know because it's been explained, but what is a collimator, this thing? What does it do?
This is going to clean the beam. When there's particles that are not necessarily in the right orbit, so that they make beautiful collisions in the experiments, we have to take them out so that they don't disturb the other particles that are in the right place. So this collimator is going to use to make this beam more clean and more protected, so that we have real beautiful collisions.
Beautiful collision is the main objective, and of course to get there, not just higher luminosity, more collisions, but also a better beam, a more performant machine. And this is what is being prepared here. I'm sure that on stage they will explain you more about the new technologies the CERN is getting ready, and some of them are already ready to go and start for the high luminosity LHC. Over to you, Claudio.
We try to do our best here. And let me now introduce our next guest, Amalia Ballarino. Thank you
Thank
for
you very
coming.
much.
Superconductor expert and working for the High LHC project. So my question is, the secret of the LHC magnet lies in a special property, superconductivity. Can you tell us more about this?
Yes. So superconductivity is a property of very special materials who are able to transfer current with zero resistance. This is fantastic because it means that we can transfer a huge amount of current in a very small cross sections. It's a fantastic property, and we may wonder if it is so good, why we do not use it already today in the everyday life. It's because the material that we are working with today are superconducting at very low temperatures. So if you think about the Large Hadron Collider, which was presented by our director of accelerator, in order to operate our magnets, which are made from niobium titanium superconductor, we need to maintain a temperature of about minus 271 degrees Celsius.
Wow.
This is a condition sine qua non in order to be able to enable the material to have this fantastic property.
And can you make some example in how that new technology can change, for example, our daily life, when
Yes.
it would be implemented in our daily life?
I think that we can start from examples which are already real of superconducting technology which is already used in everyday life. When we go to the hospitals and we need to do an image of our body, doctors use MRI, which are magnetic resonance imaging superconducting magnets. It's a technology which is a real spin-off of what we did on accelerator technology, something like 20 or 30 years ago. And we have these magnets which generate high magnetic fields which make images of our body. So I think that we can start with something which is already today used in a routine way, in an important way. When we think about our health, we know it's something important in everyday life. There are other magnets, NMR, which are even higher field, which are also used in order to study the structure of molecules. These are also superconducting magnets which are made with our technologies. So I think these are two real examples of a use of a superconductivity in everyday life.
Okay, thank you very much. You are here as our guest today. Don't be jealous, because Paola, during this time, is arrived at the Amalia's lab, transformed in a sort of magical lab today with incredible experiments. Let's see. So I think she's having fun in your
I
laboratory.
can see she enjoys it. Nice surprise.
So superconductivity might be funny because we
It is
see
definitely.
fun application.
Definitely. Actually, what you have seen are some specific demonstrations of properties of superconductivity. We use superconductor because they transfer a lot of current. We need to generate high magnetic fields, which means that we need very high currents. So we use superconductors basically for these characteristics. But what you have seen today in the lab are examples of magnetic levitations. Superconductors expel the magnetic field when they are cooled down to the temperature where they are superconducting, and you can use them for levitating above a magnet. So we had a trottinette, a bicycle which was levitating above a rail of permanent magnets, and the bicycle had on the basis high temperature superconducting materials cooled with liquid nitrogen, and it's always very fascinating to see it.
Yeah, because it's like a science fiction. A
Yeah,
few
you
years
fly.
ago it was science fiction. But let's move on. So Fred, we have seen that CERN is well advanced with the technologies for the free high luminosity LHC, but at the same time you are experimenting with new ways of accelerating particles.
Yes, we have always to develop technology for the future. So now we are, we said LHC, we will have the upgrade LHC. We have other studies we will discuss about later about CLIQ and FCC. But we have to look at the next machine, and we have to have seeds now. And we have looking plasma acceleration is a way to accelerate in a very short distance particles to high energy.
Okay, if you see around us there are some movement, machine moving. It's very nice because we are live. Everything today it's an open day event, so you can come here to see everything, to be in contact with scientists. It's very nice because we can say that science is not that far from the people. What do you think? It's because what we see here today with children playing with this machine, it means that science is very close to the people.
I think it's very good. For me, it's reassuring to see more than 80,000 people coming from these open days, all this meeting, all this rencontre of young people with us and so on. I think it's a good thing. At the time that people are saying about obscurantism, are no more confident in science, I think this is very reassuring. I think it's a very good thing. We have to open our laboratory to show to all the population, to show to the taxpayer and so on what we are doing. We have to explain. And I'm very glad to see all the people queuing hours to come and to visit CERN. This is fantastic for me, putting a big morale to work more.
So Maya, what do you think about what is happening around us today here at CERN?
It's fantastic. It's motivating for the people, but it's motivating also for us because we can see that what we do is interesting for people. We see many children that we hope will take over and will enter in our field. So I think that these open days are really a great success and a great motivation for the visitors, but also for us.
Okay, but come back now straight to the topic we were discussing about, Awake. And our special envoys, of course, have been also to interview the Awake project leader. And so, reporting from there, we have Paola and Cedric.
So we've been exploring the CERN Accelerator Complex. Exploration is done now. Let's now go into the future. We've seen the high luminosity LHC. This is much beyond. This is a new concept, a new tool. We're here with Edda Geschwendner. She is the project leader of Awake. Edda, what is Awake?
Awake means Advanced Wake Field Experiment. And it's a new way to accelerate particles, a new technology to accelerate particles to even higher energies and much faster and stronger.
So the tool is this. There is a word that is wake field. So what is the novelty? Usually particles are accelerated by a radio frequency cavity, like we've seen in the LHC. What changes now with this new idea?
So what changes essentially is that we use plasma as our medium. So it's not in vacuum that particles are accelerated, but in plasma. So how does it work? you can imagine like a boat. You have a boat which is on a lake, and this boat creates waves. And then you have the surfers which jump on these waves, and then they get accelerated. So, and that's exactly what we are doing in Awake now. So our boat is the proton beam from the SPS. Then our lake is a plasma. It's 10-meter long plasma, and you see it here in this picture, this 10-meter long plasma cell, what we have here. And then we inject the electrons, our surfers, and they get accelerated. So the advantage is that the strength of accelerating the particles is extremely strong. So we can reach up to a factor 1,000 of higher accelerating gradient compared to these conventional accelerating technologies.
And when do you think we can have an Awake accelerator ready for use for the physicists?
Well, it depends. I mean, using Awake, this Awake technology, so for using a proton beam as your boat, as your drive beam, that could be already an intermediate phase, because we could use it already for fixed target experiments. So that could be already in the nearer future once we have really demonstrated that RAN2 works. For using really linear collider, electron-positron collider, there's still a longer way to go, because we still have to demonstrate in the entire plasma wake field, not only using proton beam as a drive beam, as a boat, but also laser or electron beam. There are still some challenges and some beam quality parameters which we have to show.
This is really research at its best. It's challenging. You cannot really predict, but you proceed in steps. At each steps, you learn something new, and you apply something new, and there are also surprises. This might be even applied for technologies that are useful for us, right?
Definitely, the field of plasma wake field acceleration is something which can open many doors. I mean, in principle, it can be used for medical applications. You can use it for XFEL technologies, for many other uses. It depends then which boat essentially you are using then.
Thank you very much, Edda. And we are up. We wish you a lot of luck, not just with the Open Days, but also especially with Awake. Thank you.
Thank you.
Thank you, Paola. That's the far future, but I also heard about other projects like a 100-kilometer collider and a 55-kilometers one.
Yes. We have now, as I said, LHC up to 2023. We have the new upgrade, high luminosity LHC up to 2040. We have to foresee what we will do later. And we have study for that. We have two studies. One is a linear collider with electron-positron. One is a circular one where we can put electron-positron in the first stage and proton-proton. Then one is a click compact, also is relatively compact at CERN, linear collider. First of all, it could be 11 kilometers, accelerating electron-positron to energy of 380 GeV. It could be extended up to 50 kilometers, 25, again 25. That is the linear collider, is one option. A second option is to build a circular tunnel up to 90 to 100 kilometers. And as I said, the goal will be to accelerate proton against proton. Then as we will develop higher field magnet and bigger circumference, we could go up to 100 TeV, tera electron volt. That is more or less 7 to 8 times more than we are doing in LHC. And also we could, in the first stage, accelerate electron-positron. Then it's different machine. We will build only one, and now we have to decide in a few years which one we will do after 2040.
Okay, thanks for that explanation. Frédéric Baudry, CERN Director for Accelerator. Now, let's move on while our viewers can keep on sending questions through the social network. Let's watch this clip of a visit this morning to FCC and CLIC.
Hello. Future Circular Collider is defining a science mission up to the end of the 21st century. With the discovery of the Higgs boson, an entirely new book of physics has been opened. Now, to implement a vast particle accelerator infrastructure like this one, we really need very advanced technologies, and energy efficiency is key to the sustainability of such an infrastructure. These technologies that remain yet to be developed by us, together with industrial partners, have also plenty of opportunities for everybody's life and to make everybody's life better.
For the CERN Open Days, we're welcoming visitors to 3 sites for CLIC. CLIC is the Compact Linear Collider, which was one of the 2 main options for the next high energy frontier collider here at CERN. CLIC will collide electrons and positrons at very high energies, up to 3 TeV, and will be built in 3 stages from 11 kilometers up to 50 kilometers. Colliding electrons and positrons at very high energies lets us measure properties of the Higgs boson with great precision and gives us great sensitivity to potential effects beyond the standard model of physics that we know just now. We're standing here just now in the CLEAR beamline. CLEAR is the CERN Linear Electron Accelerator for research. It's led from some of the CLIC accelerator studies, and here we're doing research on accelerator technologies and also detector technologies that will contribute to the next collider here at CERN.
We are back to our stage here, and we have a second session of question and answer. So we have received some question for Amalia, and there is one very interesting, very long and interesting. Do you think we will ever find the smallest particle, or will detection technologies advancement always lead to discovering smaller particles?
So, yes, what we are trying to do, as we were saying at the beginning with the upgrade of the machine, is to try how we can go ahead with the search of new particles. So with the new accelerator that we are constructing, for instance, the FCC machine, we try to push our technology and go to higher fields. And going to higher fields, we will also go to higher energy for the machines, and this will give us the potential to eventually discover heavier particles. We have found the Higgs boson. We know that this was the last unknown particle, which was completely in the standard model, but we know that this is not the end of the story. So our search continues both from the technological point of view and also from the physics perspectives.
And now another question for Frederic. What is the ideal hard magnet for CERN's ongoing research? The ideal hard magnet for the CERN research. Do you have an ideal, if you can choose?
Okay, ideal one. I think what I said, the ideal situation at CERN is to have the 3 pillars, to have a set of accelerators we can operate, to have a project we are building, and to have study for the future. And we are in these ideal things. And we have now operating LHC with all the chain of accelerator I described previously. We have this HLHC project, but it is a very difficult project and will be put in place, installed starting in 2026, running in 2040. You can see our programmation is long term. And we have to do what could be our next machine after 2040. Machine could be from 2040 to 2080, 2090. And I think this is kind of ideal things that CERN should continue, and we should get support for our member state and non-member states of the country.
Okay, let's move forward because we are a little bit in late. So now let's see what kind of technologies developed here can change our life. We have a jingle for this. So we all know that WWW was invented at CERN 30 years ago. It was not a physics discovery, but it's one of the most impactful breakthroughs of CERN on our life. What are the other technologies made in CERN with the potential to change our life? We have here today an expert in knowledge transfer from CERN who can tell us more about this. Please let me introduce Anaïs Rassat. Welcome.
So there are three types of technologies that are developed at CERN that have applications outside. So CERN is obviously working in accelerator physics for everything related to accelerators, then detectors, and then all the computing facilities to analyze the data. And we find that those three types of technologies have applications outside of high energy physics, and that can be in medical applications, also in aerospace applications, and then we even have some very exciting developments in cultural heritage, which I particularly like because it seems very far from what you'd expect from high energy physics, and actually we find that to analyze pieces of art and artifacts, we can use technology that's developed at CERN.
Okay, I'm sure that Paola is going to give us more and more information about this. So let's join Paola and Cedric and take a look at Medicis. Thank you very much, Paola. Another question is, can we do technology transfer by using some of the discovery linked to the Higgs boson, for example?
Yes, that's a very exciting thought. So, what's important to understand is at CERN we're answering scientific questions, and some of those answers come with the Higgs boson. To answer those questions, we must first push the limits, technological limits, and develop technologies. Today, very concretely, we see those technologies have applications in medical, in medtech, in aerospace applications, cultural heritage. And to ask the question of this, how the scientific discoveries are going to have applications, the easiest way to answer is to look historically what's happened. And in the past, in the last century, the 20th century, for example, we've seen again and again that discoveries that have been made in fundamental research have had applications concretely that have a positive impact on society. Now, no one has the imagination yet to forecast what those applications are going to be, but everyone here has the enthusiasm to know that those applications will happen. So today, the science is the question, but the technologies is a reality. We already see applications of CERN technology with a positive impact on society.
Great, thank you very much. So if Paola is ready, we can open our next connection from Isolde.
beams available and isotopes which nobody else can provide.
So you have mechanical engineer, technicians, people that are designing the target, that are operating the targets, you have the physicists, and all those persons, they are actually managing to collaborate.
The Isolde physicists had been waiting for this upgrade for more than 10 years.
We keep on receiving questions from the social network, and we try to answer some of them. I would ask Frederick now, for example, some very, very easy, basic question, also important. For example, if we can move faster than light, what would we see, and what we see our past, for example?
We can't go faster than the light. The easy question, we can't. We will need, this is Einstein, I don't want to violate Einstein, we can't. We will need infinite energy to go faster than the speed of the light. Then we can't. Finished.
Good, very quick. So, can I have the microphone? Thank you. I have another question for Anaïs. Is CERN trying to discover a cure for cancer with the medical physics?
Okay, so we know already there are technologies developed at CERN that come from accelerator technologies, for example, that have applications in cancer treatments. And so we are currently exchanging with experts in the medical field. So at CERN, we do not do medical work at CERN, but we liaise with those experts. And those technologies are already being transferred in medical facilities.
So now if Paola is ready, we can join her in a very interesting place called Idea Square. Paola. She's not ready yet, so I would like to change a little bit our schedule, and because our surprise guest is already here, so I would like to invite, for the joy of our audience, Fabiola Gianotti here on stage, CERN Director General. Thank you very much for coming. So you have a unique opportunity today to ask questions about this fabulous place called CERN. And Fabiola, I just want to ask you, what's your first perception today? It's the first day, open day, and what you see around you is fabulous.
Yeah, it's fantastic. I've been going around through all the site that we have put in place, see many activities. It's really beautiful to see this, I would say, empathy between the public and us scientists and other personnel that is helping us with a lot of exchanges. I see families with very little kids. We see a little baby before at Isolde. So I think it's really a family event, an event where the public really shows the great interest they have for science and for technology. And so far so good.
And for you, for the scientist, what kind of feedback do you feel when you see all these children running around where you are studying, making experiments?
Children are good because our projects are long-term projects, so we have to tap into the young generations. But more in general, I'm always amazed by the great interest for science of everybody, but in particular the young generations. And the fact that people really think that it's good to invest resources also in fundamental research, in blue sky research, in knowing how the universe works. And that's the main feedback that I have. The surprise, the positive surprise, the encouragement for what we do, and many people today telling me and other colleagues, you are doing great things, and that's nice.
So if I can change a little bit our roadmap, because Fabiola Gianotti is here for a few minutes with us, and so I have some questions, and we are also waiting for the live connection with Paola. So I will ask this first question, which is somehow related to what you just said. It comes from Twitter, from Christopher, and the question is, why does CERN exist? So the fundamental mission of CERN.
Oh, it's a very good question. Thank you, Christopher. So CERN was founded in 1954, so in the aftermath of World War II, with two main goals. One was to bring back to Europe excellence in scientific research, because during the war, of course, many brains had emigrated to the US, some of them to Russia, and so Europe was a bit depopulated in terms of research, in terms of brains, in terms of excellence in science. So the great visionary fathers of CERN, politicians and scientists, understood that the resurrection of Europe would also go through research and science. And the second goal was to foster peaceful collaboration among European countries after the war that had created a lot of division. So science as a glue, science as a tool for peace, which is still very, very modern today in our fractured world, where there are a few things like science that can really assemble people and bring them together.
So there are some keywords here gathered around us. One is passion, another is knowledge, and the third one is future. Here at CERN, you are building the future of this huge laboratory. And personally, as a scientist, but also as a human being, what's your wish? What do you want to discover in the future?
I'm not surprised by your question. It's a question that I get very, very, very often. You know, what we are doing is addressing open questions. There are many, many exciting and crucial questions for which we don't know the answer from. I'm sure you have discussed the dark universe. 95% of the universe is unknown. We don't know where the antimatter went, because our universe is mainly made of matter, and many, many, many others. So for me, what is exciting is to make progress toward addressing and answering this question. Clearly, if you could mention just one thing that I would like to clearly understand in the composition of dark matter, would be great, because then our understanding of the universe will improve from the current 5% to 30%. So that's really a great leap.
Okay, perhaps now we can have the live connection with Paola. Not yet, so we move on. We have some other question to ask to our guest, and I really thank all the audiences, the one following us on the CERN social network, but also the one following us from Euronews, which is partnering this live event today. And of course, by the way, I have to say a big thank to all the people working here around the house, because they make this possible. And so, Fabiola, more seriously, I mean, you are going to stop research for some time to improve the CERN machines. And what is happening in the next months? And then what's the promises?
So we are not stopping research. We have stopped the accelerator complex in order to do some non-recurrent maintenance, and in particular some important upgrades, in particular to what we call the injectors, so the accelerators that inject the particles into the Large Hadron Collider. And this is a very important step toward the upgrade of the accelerator complex to provide, by the mid-2030s, 10 times more data than what the original LHC had foreseen. So there is a lot of work going underground, with people working in the tunnels, and it was very nice that the visitors could see what we are doing. But at the same time, of course, the experiments have recorded a lot of data from the previous operation of the LHC, so they are analyzing them and producing physics results. So it's a very busy moment. We used to say that shutdowns are sometimes even more busy periods than when we operate. And so now, with this shutdown now, and then another one around 2024, 2025, we are really going to make our, well, perhaps also go a little bit higher in energy, but mainly in improving, in increasing the intensity of the proton beam, so as to produce many more collisions, and so to be able for the physicists to study, discover rare processes, massive particles, etc.
Okay, so far we didn't find a new particles, but we find Paola, our running particle, and we lost her for a few moments. Now we found her. She's at the Idea Square. small problems of live connection. So we are back, and we hope that Paola will be back here very soon because we are waiting for her. Let's see if we have the connection again. Running particle. That's Paola today. So we wait for Paola here on stage again to end this live science show. And Paola made a great job really so far. And we are here with our two guests, Fabiola Gianotti, Director General of CERN. We have a lot of questions for you. I chosen this question. It comes from Facebook, Niranjan. And the question is, as Higgs field is responsible for the mass of fundamental particles, then is there any connection between Higgs field and gravity?
No, because the type of interaction between the Higgs field and the Higgs boson are completely different from the type of interaction that we are used to, like gravity, like electromagnetic interaction, like the weak force, like the strong force. So it's a completely different type of force. It is related to the mass of the mechanism by which the elementary particle acquire a mass through direct contact between the Higgs field and the particles themselves. It's a different type of force.
As we mentioned Higgs boson, what are your memories of this fabulous day when you made the announcement?
So it was the 4th of July of 2012, and the two experiments, ATLAS and CMS, reported the discovery of this very special particle. So Joe Incandela gave the talk for the ATLAS, for the CMS collaboration, and I gave the talk for ATLAS. It would have been good to interchange the two. But it was a great day because for me it was the accomplishment of a long path and the beginning of a new one. The accomplishment because, of course, the Higgs boson was one of the goals of the Large Hadron Collider, and we started thinking about the potential of the LHC for discovering the Higgs boson in the early 90s. Then finally, we got that particle. And then a starting point, because again, the Higgs particle is a very special one, completely different in terms of properties, we call it quantum numbers, from the other elementary particles. Also, the way it interacts, as we said before, is different. And so it's a unique door into the unknown physics, into the new physics. So studying this particle, this very special particle with very, very high precision is a must. It's also related to the most obscure particle, the most obscure part of the Standard Model, which is the theory that describes the elementary particle. So clearly, the Higgs boson can give us a lot of clues about going beyond.
Okay, another question coming from YouTube. What are the experiment and project with CERN which CERN will be working on in the coming future?
So at the moment, we are preparing the upgrade of the Large Hadron Collider, which will bring us until up to until 2037 or so. And in parallel, we are studying possible candidates for a future collider after the Large Hadron Collider. So at the moment, we are just at the level of design studies and of pushing R&D for technologies, accelerator and detector technology. So we have two different projects under investigation at the moment. One is a linear collider called CLIC, which will collide electrons and anti-electrons, so electrons and positrons, and will have a length from 11 kilometers in the first stage up to 50 kilometers. And the other one is called Future Circular Collider, FCC. It's a ring like the Large Hadron Collider, but much bigger, 100 kilometers instead of 27, which will allow, again, also electron-positron collision, but also proton-proton collision like we are doing at the LHC, but with 7 times more energy. So these are the colliders we are studying, but of course in parallel we are also exploring other experiments in the rest of the CERN accelerator complex, in the so-called injectors, that will have a physics reach that is complementary to high-energy colliders.
I would like to ask you something not directly related to science. I mean, what do you want to deliver as a message to all these children that are here today and they will be here tomorrow because of these open days?
So, on a personal level, I think that there is nothing more rewarding and exciting than contributing in our little kernel to advance the knowledge of humanity. If in our day-by-day work we can do even very tiny steps to increase the knowledge of humanity in science and in technology, for me that's just great. And second, there is also nothing so rewarding as learning. Learning every day something new. For me, you know, I am very, very lucky because in my scientific career at CERN, and even today as director of CERN, there is no single day when I go home in the evening and I said myself, gee, how much I learned today. So that's very nice.
That's a really great message. I would like to invite here on stage all our guests because we are arrived at the end. We are trying to detect the Paola particle here around, but perhaps she's a bit late because we are waiting for her, but we are really in late. So I want to thank everybody, all the people who work for this live show, and also all my guests today. And it was a very amazing experience. I hope you share the same pleasure on the social network from CERN and from Euronews. So thank you very much to all of you. Thank you very much for your job, for all these people who are enjoying CERN and science today. And thank you very much to Paola. Thank you, Paola. Grazie. Ciao.
Okay, very nice. Thank you. Grazie Claudio. Grazie mille. Grazie Claudio. Grazie Claudio. No?